Welcome, guys. In this video, we are going to study a method that is going to help us to use derivatives to find limits, known as LHopitals Rule. Let's take a look at the limit of a form of ratio of two functions when x is approaching to a of f of x over g of x. And let's assume that both these functions approach to 0 when x is approaching to a. Here are some examples of indeterminate form of type 0 over 0. So limit when x is approaching to 1 of x squared minus 1 over x minus 1. So when x is approaching to 1, numerator and denominator, both of these approach to 0. Similarly, sine of x over x is in indeterminate form of type 0 over 0. And 1 minus cosine of x over x is also in form of 0 over 0. Now let's assume that functions f and g of x, they are differentiable, and let's assume that their derivatives are continuous at point A, and let's also make an assumption that g prime at point A is not equal to 0. Then we can use local linear approximation to approximate these two functions using their tangent lines near point A. And let's also assume that this limit here is in indeterminate form of 0 over 0, such that f of x is approaching to 0 and g of x is approaching to 0 when x is approaching to a. Then those two values, they are approaching to 0, so this limit takes the form limit x is approaching when x is approaching to a, f prime at a, x minus a over g prime at a, x minus a. So canceling out those two values, we'll end up with the following expression, with the following ratio. So we can replace a limit when x is approaching to a of ratio of two functions with limit when x is approaching to a with their slopes, with the slopes of their tangent lines at point A. So the following theorem is going to summarize our findings above. So here is a statement of LHopitals rule in a case when we are working with indeterminate form of 0 over 0. Let's suppose that functions f and g are differentiable functions on an open interval containing x is equal to a, with an exception of possibility that they are not differentiable at point x is equal to a. We are going to use that in a second. And let's assume that limit when x is approaching to a of f of x and g of x both are equal to 0. So we have a determinate form of type 0 over 0. And if limit when x is approaching to a of the ratio of their derivatives exists, or if this limit is plus or minus infinity, then we can switch limit when x is approaching to a of ratio of those two functions, f of x over g of x, with the ratio of their slopes of tangent lines at point A. All right, so also this statement is also true in the case when we are working with one-sided limits or when x is approaching to plus or minus infinity. All right, now let's use LHopitals rule to solve a couple of limits. So previously, if we were to solve these limits, we would algebraically try to factor out terms in numerator or denominator, try to cancel out some zero terms. Now we can simplify our solution by quickly taking derivatives of denominator and numerator and looking at their ratio instead. So here, derivative in numerator, this is 2x. Derivative in denominator is 1. So when x is approaching to 2, this limit is equal to 4. Now let's take a look at the following limit. First, let's confirm that this limit is indeterminate form of 0 over 0. That is true. Tangent of x is approaching to 0 when x is approaching to 0 from the left, and x squared is also approaching to 0 when x is approaching to 0 from left. All right, so then we can use LHopitals rule. Derivative of tangent of x is secant squared of x. Derivative in denominator is 2x. When x is approaching to 0 from the left side, secant squared of x is going to approach 1. Derivative in denominator is going to approach minus 0. So this is small negative value. Then that limit is equal to minus infinity. Now, LHopitals rule also works in a case when we have indeterminate form of type infinity or infinity. So again, let's assume that we have a ratio of limit of ratio of two functions f of x and g of x when x is approaching to a. Then we can switch that limit with the limit of ratio of their slopes of tangent lines when x is approaching to a. Now, however, in this case, a limit when x is approaching to a, f of x and g of x is equal to infinity. This notation here means that if we were to elaborate more, this notation here means that those limits can approach plus or minus infinity. So it will work for any of these cases when we have infinity over infinity. So either it's plus infinity or minus infinity, or minus infinity or plus infinity, or minus infinity or minus infinity. All these cases are covered by this theorem. All right, now let's use the theorem to solve a couple of problems. So first, let's confirm that this limit is in indeterminate form of infinity or infinity, which is true when x is approaching to plus infinity. In numerator, x is approaching to plus infinity. In denominator, e to the power of x is also approaching to plus infinity. Now, using LHopitals rule here, we can switch that limit with the following one. Derivative in numerator is 1 over e to the power of x in denominator. When x is approaching to plus infinity, that limit is equal to 0. Now, next limit here is, first let's confirm that this is in indeterminate form of infinity or infinity when x is approaching to 0 from the right side. In numerator, we have minus infinity. And in denominator, we have 1 over sine of x, which is plus infinity. Then using LHopitals rule, we can switch that limit with the following one. Derivative in numerator 1 over x. Derivative in denominator is minus cosecant x cotangent of x. All right, now let's try to work a little bit more. Since in numerator we have infinity, in denominator we have a 1 over sine, which is infinity, and cotangent cosine over sine. This is also infinity. So we're not done yet. Then let's express this as the following limit. This is 1 over sine, so getting sine in numerator, we have sine of x over x, minus in front, and cotangent is written as tangent in numerator. Okay, when x is approaching to 0, when x is approaching to 0, this is approaching to 1, and tangent of x is going to approach to 0. All right, so that limit is equal to 0 then. Now we can also use LHopitals rule to study growth of an exponential function. Let's take a look at the ratio of the following. Let's take a look at limit of the ratio of the following functions: x to the power of n over e to the power of x. Now taking derivative here one time, we can switch this limit with the following one: n x to the power of n minus 1 over e to the power of x. Now we are not done yet. Here we can apply LHopitals rule one more time. So small note here: if using LHopitals rule once doesn't work out, and then if you have a limit of indeterminate form of 0 over 0 or infinity again, then you can use LHopitals rule one more time. Then we have n multiplied by n minus 1, x to the power of n minus 2, and e to the power of x in the denominator. Then we can apply the LHopitals rule one more time, again confirming that this is in indeterminate form of infinity over infinity. We can do that operation n times, and we'll end up with n factorial in numerator over e to the power of x in denominator. So that limit is equal to 0. And then in this limit here, applying the same procedure, eventually we'll end up with the following limit: when x is approaching to plus infinity, e to the power of x over n factorial in denominator. So, which is equal to plus infinity. So what we found out here is that exponential function always grows faster when x is approaching to plus infinity rather than x to any power. So indeterminate forms of type of 0 over 0 and infinity over infinity that we have studied so far are not the only types of indeterminate forms. So when we are working with limits, we often end up with conflict of the following functions: f of x and g of x. So for instance, the ratio of those two or product of those two. For instance, here, the ratio of those two functions gives the rise of indeterminate form of type 0 over 0 or infinity over infinity. However, if we are working with product, this can also give us a conflict like 0 multiplied by infinity, f of x to the power of g of x, for instance, can give us indeterminate form of 0 to the power of 0, for instance, or let's say 1 to the power of infinity, and etc. We are going to study some of this in a second. For instance, f of x and minus g of x can give us indeterminate form of type infinity minus infinity, or for instance, minus infinity plus infinity. Now let's take a look at indeterminate form of type 0 multiplied by infinity. We do not have a special case of LHopitals rule in that case, but what we can do is we can try to bring this indeterminate form of type 0 multiplied by infinity into either 0 over 0 case or infinity over infinity case. And then we can use LHopitals rule and proceed. All right, now let's take a look at the following two limits. First limit is when x is approaching to 0 from the right side, x multiplied by ln of x. Now we can bring this into one of these two types, either using the following form, ln of x over 1 over x. So that is in indeterminate form of minus infinity over infinity. So this is in indeterminate form of infinity over infinity. Or we can also express this as limit when x is approaching to 0 from the right side of x over 1 over ln of x. Okay, so here in numerator is approaching to 0 and denominator is approaching to 1 over minus infinity, so 0, 2. So we can bring this product here of 0 by infinity into one of the indeterminate forms of infinity or 0 over 0. Then if we need to make a choice, just choose the one where you can easily find the derivative. So in this case, it's easier to work with this indeterminate form because finding derivative in that case will be easier. All right, so here we have limit when x is approaching to 0 plus, then derivative of numerator is 1 over x, derivative of denominator minus 1 over x squared. So this is then limit when x is approaching to 0 of minus x, which is equal to 0. All right, now second limit here. Now let's confirm that it is in indeterminate form of 0 multiplied by infinity. So when x is approaching to pi over 4, this is 0, and 1 over cosine of 2x. When x is approaching to pi over 4, we have 2 multiplied by pi over 4, so cosine of pi over 2 is approaching to 0. So we have 0 multiplied by infinity. Now let's bring that either to the form of 0 over 0 or infinity over infinity form. So we'll end up with limit when x is approaching to pi over 4. Let's keep 1 minus tangent of x in numerator. Let's move that, let's express that as 1 over cosine of 2x. Okay, now when x is approaching to pi over 4, denominator goes to 0 and numerator also goes to 0. So we have indeterminate form of type 0 over 0. So then taking derivative, we can switch that limit with the following one. So minus second squared of x over minus 2 sine of 2x. All right, so let's try to simplify that. We'll end up with limit when x is approaching to pi over 4. So in numerator, we have 1 over cosine squared of x. In denominator, we have 2 sine of 2x. When x is approaching to pi over 4, denominator goes to 2. When x is approaching to pi over 4, numerator goes to 2 over 4. So this limit is then equal to 1. Now, next indeterminate type of infinity minus infinity arises in the case when we subtract plus infinity minus plus infinity, or add plus infinity with minus infinity, or subtract minus infinity from minus infinity, or add minus infinity to plus infinity. However, in these types here, infinity plus infinity or infinity minus infinity, all these 4 cases are not indeterminate, since this is simply plus infinity, this is simply minus infinity, and so on. All right, now let's take a look at the following problem. Now, this is in indeterminate form of 1 over 0 plus, which is plus infinity, minus 1 over sine of x when x is approaching to 0. So this is also plus infinity. So this is of indeterminate form of infinity minus plus infinity minus plus infinity. All right, we do not have another L'Hopital's rule in this case, so we will try to bring this expression here to the indeterminate form of 0 over 0 or infinity. So this is then limit when x is approaching to 0 from the right side of sine of x minus x over x sine of x. So bringing that into the common denominator, we brought this into indeterminate form of 0 over 0. Now, using L'Hopital's rule here, we'll end up with limit when x is approaching to 0 from the right side of cosine of x minus 1 over sine of x plus x cosine of x. Okay, now when x is approaching to 0, we have 0 in numerator. When x is approaching to 0, we have 0 here plus 0. So we are again ended up with indeterminate form of type of 0 over 0. So we can use L'Hopital's rule here one more time. So we'll have limit when x is approaching to 0 from the right side of minus sine of x over 1 over cosine of x plus cosine of x minus x sine of x. All right, now let's see what do we have here now. When x is approaching to 0, numerator goes to 0. A denominator, we have this is 1, this is 1, this is 0. So that limit is equal to 0 then. Okay, now next indeterminate forms that we are going to study is a form of 0 to the power of 0 or infinity to the power of 0 or 1 to the power of infinity. In all of these cases, again, we do not have new L'Hopital's rule, so we need to try to bring that into the form of 0 over 0 or infinity over infinity. Now, one suggestion would be, so for instance, if we have f of x to the power of g of x, let's call this as y. Then to bring this into the form of 0 over 0 or infinity, we should try to take a ln from both sides. So we'll have g of x multiplied by ln of f of x. And then we can express that as ln of f of x over 1 over g of x, or g of x over 1 over ln of f of x. Whichever will be easier to work with, whichever function will be easier to take derivative from, you need to make the choice later on. Now let's take a look at the following limit. This is a limit that we have seen before. We know that it is equal to e. Let's use L'Hopital's rule to show why it is equal to e. So that limit is in indeterminate form of 1 to the power of infinity. Okay, so let's call this expression as y. So 1 plus x to the power of 1 over x is equal to y. Now taking a ln from both sides, we have ln of y is equal to ln of 1 plus x over x. Now taking limit when x is approaching to 0 from the right side from both sides. And then we can see here that this limit here is indeterminate form of ln of 1 is 0 over 0. So we can use L'Hopital's rule here. Since that limit is equal to limit when x is approaching to 0 from the right side of 1 over x, 1 over 1 plus x in numerator and 1 in denominator. So that limit is approaching to 1. Okay, so we found that limit when x is approaching to 0 from the right side of ln of y is equal to 1. Now we know that ln is a continuous function in its domain, so we can switch limit and ln. So we have limit, ln limit when x is approaching to 0 from the right side of y is equal to 1, taking both sides to the power of e, will have a limit when x is approaching to 0 from the right side of y is equal to e to the power of 1, so e. So we have shown that this limit is equal to e. Right, next limit here. So when x is approaching to 0, that expression goes to 1, and this is to the power of infinity. So we have indeterminate form of 1 to the power of infinity. Now again, using the same trick, calling this as function y, taking ln from both sides, bringing this power down, we'll have ln of 1 plus sine of x over x. Now taking limit from both sides, limit when x is approaching to 0, limit when x is approaching to 0. Okay, so denominator goes to 0, ln of 1 goes to 0, so this is in indeterminate form of 0 over 0. We can use LHopitals rule here. So we will end up with cosine of x over 1 plus sine of x over 1. Okay, so we can simply switch this here. Okay, now when x is approaching to 0, numerator goes to 1, denominator goes to 1, so that limit is equal to 1. So limit, or let's switch limit with ln again. So we'll have ln limit when x is approaching to 0 of y is equal to 1, which means that limit when x is approaching to 0 of y is equal to e. So that limit is equal to e. All right, guys, now this concludes our section on indeterminate forms and LHopitals rule. Thank you for watching.